So today we're going to talk about the Maxwell Boltzmann. Now the Maxwell Boltzmann is a plot of the number of molecules against the energy. So it's the number of molecules at any point on this graph, it's the number of molecules with that particular energy. So at this point here, it's however many molecules this relates to at this energy, okay? It is important that this line, this plot, never crosses the y-axis, and that's because we can't say that any particles have zero energy, okay? So we can't say that particles have zero energy, and that's just kind of a fact that we know, so we need to make sure that we don't cross over, or even worse, cross over the y-axis and we start saying that there are a fraction of particles with a negative energy, which isn't something that we can talk about, okay? So it always can start at 0, 0, so at the origin, okay? One thing that is important, and here's a fresh Maxwell Boltzmann, one thing that is important while working with Maxwell Boltzmann in exams is that the labelling of the y-axis. So at the minute, this just says number of molecules. Now, what you need to do in exams, and they are very explicit about this, is you need to be a bit more particular than just saying the number of molecules or the number of particles. So for instance, if a question was around Maxwell Boltzmann being used to explain the relationship between the rate and the concentration of chlorine molecules reacting with hydrogen molecules, but an excess of hydrogen molecules, then actually it's the chlorine molecules that we are interested in, okay? So rather than just say the number of molecules, we'd have to say the number of Cl2 molecules. The number of whichever particles, okay? You need to be aware that you need to be that specific when you're talking about what's on the y-axis. So it's very important, okay? And just to remind you, never crosses the y-axis. So again, another fresh Maxwell Boltzmann to look at. This time, I'm just going to think very quickly about what this area underneath this Maxwell Boltzmann graph actually is. So if you have this whole area under here, what does it actually represent? Well, the Maxwell Boltzmann, and for reasons that go beyond A-level chemistry and A-level maths even potentially, you don't need to understand why this is, but you do need to know that the area underneath the Maxwell Boltzmann, so the area underneath the Maxwell Boltzmann, or underneath the curve, is equal to the total number of particles. Okay, so it's equal to the total number of particles. The total number of particles, and that often comes up as a very short 1 mark question in the multiple choice section. So make a note of that, try to make sure you commit that to memory, that the area under the graph is equal to the total number of particles. It's not equal to the total energy of the system, which is the common mistake that they make, and it is also a common wrong answer that they put alongside the total number of particles to try and trick people. So we know from previous lessons that for a reaction to happen, that the particles have to collide with enough energy to react, and we call that energy, the minimum energy for a reaction to happen, the activation energy, okay? And we remember we label that capital E, A, okay? And actually we can plot this on the energy on the x-axis. So for instance, if our activation energy was this amount of energy, we call that EA. Now, when you look there, what that actually shows you is that the vast majority of the particles, all of the particles on this side, have not got enough energy to collide and react. And actually, a very small proportion of the particles, these particles over here, have got enough energy to collide and react. And it's very important Remember, that is going to be the case for the vast majority of the time. There's ways we can move that activation energy, and there's ways we can move the shape of this plot to try to make sure there are more particles on the side above the activation energy. And we'll talk about that more as this lesson goes on. There are another kind of two key things we can label on the energy axes or on the x-axis. So, of course, like I say, we've got for the activation energy, EA, and then there's two other energies we can talk about. We can talk about the average or the mean energy, and we can talk about the most probable energy, or most probable energy for a particle to have. Now, so these two things, if it was a normal distribution, if it was just a normal bell curve, would be in the same place. That's a very badly drawn normal bell curve, but it would be in the same place. They would be here at the top of the peak. But it's not a normal distribution. It's slightly skewed. So the most probable energy is still in the same place. So the most probable energy is the top of the peak, and we'll label that MP for most probable energy. But the average energy, because there aren't as many particles on the left-hand side of that most probable energy, there aren't as many particles with a low energy. Most particles have an intermediate energy or a high energy. The average is actually skewed slightly to the right. So the average energy, or the mean energy, is skewed slightly to the right of the probable energy. So the mean energy is skewed over to this side, or the average energy. I've seen it referred to as the average and the mean energy. I've seen it as the mean energy in the exam questions I was looking at before this lesson, so potentially we'll call it the mean energy, okay? And that's because there's less particles on this side and more particles on this side of that probable energy point, of that peak in the center. So it's important to remember that the mean energy is slightly to the right of the most probable energy. Now, they will ask these in multiple choice questions. In fact, I've got one to show you in a second. Remember that when you're talking about energy, energy is on the x-axis. So any labels for the most probable or the mean should be on the x-axis, okay? So it should be here. Say that was labelled A, that was labelled B. It shouldn't be on the y-axis. So that's actually the number of molecules. So if this was C and D, these two should not be your answer, because you're talking about the energy, which is on the x-axis. So like I said, these are the kind of questions they like to ask. Total marks, 1 mark, quick multiple choice questions. So the Maxwell Boltzmann distribution of molecular energies in a sample of gas at fixed temperature is shown. Which letter represents the mean energy of the molecules? So let's just highlight that key word there, the mean energy of the molecules. Now remember what we just said only moments ago, I know, is that energy is on the x-axis. So we're talking about the x-axis here. So actually A and B, already we know it cannot be A and B, because they are the number of particles, they're not the energy. Now the mean energy in molecules, that is the average energy in molecules. So you've got to pick C or D. In fact, take a few seconds now. You can pause the video. Just think, which one would you pick, C or D? And I will go through the answer in a moment. So the answer is D. And the answer is D because, as we talked about very recently, the particles to the left of the peak are less. There are more particles to the right of the peak, and therefore the average energy is shifted slightly away from this top of the peak, which is the most probable energy, towards the right. So this here, over here, is the most is the mean energy. Okay, so there are two key factors and potentially a third one, which we will talk about as well, that can change the look of the Maxwell Boltzmann distribution. And those three factors are, the first one is temperature. So if we increase the temperature, we're going to increase the energy of the particles, and we'll talk a little bit about what that does to the graph in the second one. The second one is using a catalyst, and we know that a catalyst reduces the activation energy, so we'll have a look at what that would do to the graph. And the third one I've not seen them ask questions about, but I am going to go over, is the idea of pressure and concentration, and we'll talk about those two together. So there are three kind of key factors, two that are really important, and two that are really important are these first two. So the temperature and the catalyst, they're the really important ones. And the third one, which we're just going to talk about very briefly so that you have an idea about what that would do. So we're back with our Maxwell Boltzmann. We're going to say that this line is already drawn is the line for temperature 1. It's in black there. So we're going to draw a line for temperature 2, and temperature 2 is going to be greater than temperature 1. So what effect would that have on this Maxwell Boltzmann graph? Well, if you're increasing the temperature, you're increasing the energy of the molecules, or you're potentially increasing the energy of the molecules. Now what that means is that your most probable energy is going to shift further to the right. It's going to be higher, and actually your mean energy is also going to be higher, but the number of molecules is still the same. So although the energy is going to be higher, we're going to end up with a graph with a peak that's slightly lower, but a slightly broader peak, and it's going to look something like this. So you're going to have a line going up inside here, slightly broader peak, coming down, should be a little more, things like that, over to the right. And it will continue, and the same with T1, these would continue almost infinitely, okay? Now, if we look at that, the most probable energy was here to start with, has now been shifted to here, to the right, okay? And the mean energy, which maybe was here, has been shifted to the right as well, which means that our particles have got more energy. On average, are most likely to have more energy. What we could also do is we could label the activation energy. So let's say that this is the activation energy for this reaction. Now, we can easily see that we started off with only these particles above the activation energy, but now we have far more particles above the activation energy. So that explains why the rate of reaction increases. We increase the temperature, okay? So this is moved from here to here, to here, and this is moved from here to here. Why is it important that the peak goes down slightly? Well, the area under the graph, remember, is the total number of molecules, total number of particles, and that number hasn't changed. So actually the area under the graph needs to be the same as it was at the start. So for higher temperature, we do a lower peak, but a broader peak shifted to the right slightly. Notice as well, and it's important, that this only crosses the previous line once. It does not cross it again, and that's important. That is a marking point in the exam, is that it only has 1 point of crossing the original line. So this time, let's think about a catalyst. Now we know a catalyst lowers the activation energy. Okay, so let's start with our original line. So this is our original. So we've got EA in black without a catalyst, and let's use the red for EA with catalyst, and we'll see what happens. So let's start with our activation energy is, let's say it's here. This is our EA, and at this point only these particles are able to react, which is a very small proportion of the particles, the total number of particles. However, if we add a catalyst, the activation energy is decreased, so it's shifted to the left, and let's put our new activation energy over here. That's our new activation energy, and now a far greater number of particles, all those ones that were originally in there as well, a far greater number are able to react with sufficient energy, and that's extremely important. That's the bit that's important. Remember, collision theory, they have to collide with sufficient energy, which is greater than the activation energy, for a reaction to take place. And this has got a far greater proportion of those particles, of those molecules, able to react than before the catalyst was added. Finally, we talk about pressure, concentration, really pressure, because Maxwell Boltzmanns are only for a gas, but the same findings can be kind of inferred in a liquid. It's not the same in a reaction with liquids, but you can use the same kind of principles to guide your understanding of the rate in liquids. So for pressure, well, really you're saying you're adding more particles in. So if you're adding more particles in, so if the pressure is increasing, that's when you're talking about having more particles in the same volume, you end up with a graph that has the same shape as the previous graph, starts at the origin still, but should be roughly the same shape, but with a larger graph, roughly the same all the way through. So actually increasing the pressure, again, if we were to put our activation energy on here, so let's say this is our activation energy, at the start we only had a small number of particles able to react, but when we increase the pressure, we've now got a larger proportion, or a larger, not a large proportion, the same proportion, but a larger number of molecules able to react. Okay. Again, I've not seen that question come up, and I haven't found any past paper questions on it, but I think it's worth knowing and having an idea how that works. I'd like you to pause the video here and go and have a go at the exam questions that are linked through Exam Pro. There are a couple of longer answer ones and then some multiple choice ones there for you, and we'll go through the answers when you are done. So here's the first question. Now, you've got a Maxwell Boltzmann here, and it's just labeled number of molecules. Actually, it's the Maxwell Boltzmann I was using for the other questions. And it says, on the same axes, draw a curve for a sample at a lower temperature. Okay, so this is going the other way. So we said for a higher temperature, we would shift to the right, and the area underneath had to be the same, so it would have to be a lower peak. If you're going for a lower temperature, the area underneath the curve, the graph needs to stay the same, the curve needs to stay the same, but your peak, your most probable energy, is going to go down, so it's going to shift to the left. So again, we start at the origin here, and we go up into a much higher peak that comes down. That's a very poor drawing, sorry, and then should remain underneath the other line. So remember, it only crosses once up here, and it remains under peak. Yours will be a much neater peak than mine. Sorry, again, drawing on a tablet is not ideal for this. So explain the effect that lowering temperature would have on the rate of reaction. So, for the mark for that first one, that the curve is over to the left and is higher. That is your first mark, and that it only crosses once is your second mark. For the second part of this question, explain the effect on lowering would have on the rate of reaction. So the rate of reaction would decrease. So the rate would decrease. Now you don't get a mark for stating that, but it's worth stating that the rate would decrease. And the reason for that is that fewer particles have energy greater than EA, so fewer particles have energy greater than or equal to the activation energy, so there are fewer, and it's this key phrase, successful collisions. If there are less successful collisions, then the rate of reaction decreases. So here is that kind of one question. I don't think I mentioned it earlier, but there is sort of one question I've seen that talks about pressure, and this is it. So deduce the change that was made to the reaction conditions. So in the first sample, you've got more molecules than in the second sample. So what would do that? Well, the only thing that would do that is reducing the pressure. So reducing pressure. So there's been a reduction in pressure, and that's why the graph has kind of shrunk slightly. It's got smaller. So what effect has that had on the rate of reaction? Again, the rate decreases, and you don't get a mark for saying the rate decreases, but it's worth stating that, and in fact you do have to state that in this question. And the reason for that is that the particles are spread further apart. So the particles are spread further apart. So therefore, there are less collisions. Okay, fewer collisions, so fewer successful collisions. Fewer successful collisions. Okay. So a very similar question. You'll see that actually the questions kind of follow a very similar vein. Often you have to sketch a graph and then explain some of the intricacies of what's going on. So the first thing, sketch a second curve on the graph to show the distribution of molecular energies in the mixture at a higher temperature. So higher temperature, we know it's going to start at the origin again, it's going to be a lower peak, and it's going to be a broader peak than originally. It can only cross, again, the axis, not the axis, the curve once, and it should end above the EA. It shouldn't curve upwards at the end, and that's important. That you can't have a curve upwards at the end. It needs to be a curve going down. Mine's sort of there, not quite as good as I would like it to be. Explain with reference to both curves on the graph how a small change in temperature leads to a large change in the rate of reaction. So the area you're looking to talk about here is the area underneath, or to the right and underneath your curve, after, to the right of the activation energy. So the area, so the number of particles with an energy greater than or equal to the activation energy has gone up. Therefore, the chance of, there is a large increase in the number of successful collisions per unit of time. Therefore, an increase in the number of successful collisions per second as a unit time. Okay, very poorly written, sorry, per second. And that's the answer to that one. So you get a mark for the number of particles with an energy greater than the activation energy is increased, and a second mark for saying so the number of successful collisions per second has increased. Okay, so to answer the next part of this question, you need some information from the previous slide. So I've just copied that over. So you've got the reaction and you've got the enthalpy change. So delta H, that is, equals minus 90. So state and explain the effect of higher pressure on the equilibrium yield of methanol. So this is all about reversible reactions. So state and explain the effect of higher pressure on the equilibrium yield of methanol. Well, we need to look at the number of moles on each side of the equation. So to look at the number of moles on each side of the equation, we've got 3 moles on this side, 1 mole on the product side. So on the left there are more moles, on the right there are less moles. Therefore, increasing the pressure is going to shift away from the side with the most moles to the side of the less moles. So it's going to shift it to the right to the product. So it's going to increase the yield. And the reason for that is because there are more molecules on the left or fewer molecules on the right. More molecules on the left or on the reactant side. So therefore equilibrium moves to the right to decrease the pressure. So therefore equilibrium shifts to the right, and therefore towards the products, so our yield increases. What about temperature? Well, it's got a negative enthalpy change in the forward direction. So if I'm increasing the temperature, I would increase the rate. So higher temperature, like we talked about recently, increases rate. But the forward reaction is exothermic, so that wouldn't be favoured by higher temperature. The backwards reaction, which must be endothermic, would be favoured by higher temperature. So if the backward reaction would increase, if the backward reaction would increase, then the yield would decrease. Because it is favoured, the backwards reaction, the yield decreases. The yield would decrease because the backwards reaction is favoured. Okay. So the last thing to add to that then, and I haven't got space to write it, so you'll have to just add it to your own, is that therefore the temperature of 300 degrees C is a compromise, because I could get more yield by going at a lower temperature, but I would decrease my rate, my reaction would take much longer. I could get a higher rate by going at a much higher temperature, but I'd get a much lower yield. So it's a compromise between the two, the rate and the yield, which is often what you find in industry. Okay, so we've done this a few times now. On the diagram, sketch the distribution for the same sample of gas at a higher temperature. So we have to start at the origin. That's really important that we start at the origin, which I failed to do twice there. Let's get rid of that, start again. So I need to start at the origin. I need to cross over R1 once. It needs to be a lower peak shifted to the right, and then you need to try to follow roughly the same sort of shape as the remainder of the graph. It's not bad, it's not perfect, it's not bad. Remember that our most probable energy has been shifted to the right, and our average energy has also been shifted even further to the right, or not even further, but it's slightly more right of our most probable energy there. Now, let's have a look. So with reference to Maxwell Boltzmann distribution, explain why an increase in temperature increases the rate of a chemical reaction. So we've already answered this once. We know now, hopefully, what the answer should be and what it should look like. So the answer for this one is that the increase in the number or the proportion of molecules with energy greater than the activation energy. And again, that's because this area to the right has increased significantly from that starting point. Okay, so that area to the right underneath the graph, which gives us the total number of particles with energy greater than the activation energy, has increased, and therefore there are more likely to be successful collisions. So the last bit of this, dinitrogen oxide, N2O, is used as a rocket fuel. Data in the table below shows how the activation energy for the decomposition of dinitrogen oxide differs with different catalysts. Use the data to deduce which is the most effective catalyst for this decomposition. So you're looking for the one that reduces the activation energy the most. So the one that reduces the activation energy the most is this one here. That's got the lowest number. So that is iron. So the answer is iron. Explain how catalysts increase the rate of reaction. So catalysts provide, and this is a key phrase. Ooh, let's get rid of that and start that again. Catalysts provide an alternative reaction pathway sorry, I'm writing the controls. Provide an alternative reaction pathway, and that therefore that has a lower activation energy. therefore there are more likely to be successful collisions. So the last two questions we're going to look at are some multiple choice questions that we're going to look at in a second. So here are the last two questions, Maxwell Boltzmann distributions, similar to what I was talking about earlier when we had a look at the first one. So which statement is correct for the higher temperature in this second graph? So the area under the curve to the left of the activation energy decreases. The total area under the curve increases. The activation energy decreases, or more molecules have the mean energy. Okay, so there's some that we can discredit kind of very quickly. So we know that the total area under the curve is going to be the same, so that one isn't true. And we know that the activation energy is still in the same place, so that one isn't true. So now we've got this decision. The area under the curve to the left of the activation energy decreases, or the more molecules have the mean energy. What do you guys think? Let's take a moment to think about it. So have a few seconds to think about it if you haven't done these questions already, and then we'll go through it. Okay, that should be enough time. So the area under the curve to the left of the activation energy, does that decrease? Well, if the total area under the curve is the same, and we definitely know that the area to the right has increased at the higher temperature, then yes, the area under the curve to the left has decreased. So that is the correct answer. More molecules don't have the mean energy. The mean energy has moved, in fact, so you've actually got a similar kind of situation to what you had before. The question is about, this second question, is about Maxwell Boltzmann distribution of molecular energies in a sample of gas shown in the following figure. What does the area under the curve represent? We've said this a few times. It is the total number of particles. Lots of people make the mistake of going for this first answer. That's like it's like they're trying to catch people out with that one. They know that people make that mistake, so it's really important that you guys remember that that is not the correct answer. The total area doesn't tell us the total number of particles can react to each other. Remember, to react to each other, they have to have more energy than the activation energy, so that would just be the area to the right of the activation energy. And the total number of particles that have the activation, also the area to the right of the activation energy, not the whole graph. So that is all of those questions answered. Let me know how you did, and we will catch up and look at some other bits and pieces next lesson.